In this video, I'm going to tell you about some tools for working with large data sets. Here are some examples of what you might do with such tools. For example, you might have a dataset consisting of 1 billion images in various formats, and you want to convert them all to JPEG because you have GPU-accelerated JPEG decoder in your deep learning pipeline. Or let's say you have 8 million videos downloaded from YouTube, and for training a deep learning model on them, you want to split them into 10-second clips, rescale each clip to 256 by 128 pixels, and then shuffle the clips. You might want to perform offline augmentation, where you take a dataset like ImageNet and compute rotated, scaled, and otherwise modified variants of each image ahead of time, and you want to do that 100 times for each image. You might have a collection of scanned books and pages, and you might want to use an existing OCR engine to generate training data for a new OCR engine. You take each of the scanned pages, you run the OCR engine over each page, analyze the OCR output, and extract word images and shuffle the resulting word images for 30 million pages or even more words. These are all tasks that have been done with just a few lines of shell scripting using the tools that I'm going to show you. There are no complex server frameworks to install, no software library APIs to learn. All you need is a couple of command line programs and whatever job queuing system you like. We use Kubernetes. For large-scale computations like this, there are two different compute environments you typically work with. Your local machine is useful for testing and processing datasets up to a few terabytes, if the processing steps aren't too expensive. In the cloud or in clusters, you can use thousands of cores, but you have to deal with the complications of distributed processing. Network files tend not to work well in such an environment. You probably have to use object stores. Low-cost cluster and cloud nodes tend to have little local storage available, so you need to avoid using a lot of local storage. In a typical workflow, you test and debug locally, and then later move the processing pipeline to the cloud or into the cluster. In approach 1, you configure a MapReduce cluster like Hadoop locally or in the cloud. You may have to ask your local DevOps guys for help. Then you convert your dataset to Parquet or TensorFlow format. Then you write a MapReduce job. You may try this in Java, which is the native framework for a lot of these tools, or you may try it in Python, but you'll have to install a bridge and deal with the performance issues. Then you launch your job. Afterwards, you keep your eyes glued to various status pages to make sure that the job is running and to look at log outputs. And you keep your fingers crossed that nothing crashes, or you may have to start over. In approach 2, you create tar archives of the files in your dataset. Then you write a small shell script to get the job done, using any tools you like. For most data pre-processing tasks, there are already good scripts for doing them. You just need to be able to run them over your dataset. You test your script locally, and then you can keep the data wherever you want, local disk, object store, cloud storage, and you run the shell script wherever you want, locally, on a local cluster, in the cloud, using Kubernetes or Slurm or whatever job queuing system you like. I'm going to tell you about approach number 2. What I'll show you is simple command line tools that you can compose using standard pipes to get most large-scale data pre-processing tasks done quickly and easily. They're based on a couple of self-contained executables that you can compile locally and then move to wherever you need them. I'll show you how to scale up using Kubernetes or other kinds of job queuing systems. And all of this works the same locally or in the cloud because it doesn't actually require any kind of file system mounts. All it requires in terms of remote access is HTTP. In previous videos, we looked at data storage formats for deep learning. And recall that we store data sets for large-scale deep learning in sequential file formats because that improves efficiency. Now, POSIX tar files are a particularly simple sequential file format, and they're well suited to deep learning because most of the training data for deep learning comes in the form of individual files. Now, the convention we adopt for storing training data in POSIX tar files is that all the files with the same base name belong to the same training sample, and all the files belonging to the same training sample must be adjacent in the tar archive. That's all. That's all the conventions we need in order to get efficient sequential processing. So let's quickly look at a very simple file-based processing script. This script goes through a file system tree and converts all the JPEGs in there to PNG using the ImageMagick Convert program. Now, this is a fairly simple and familiar way of processing files. Note that it isn't actually quite correct the way it is written because it doesn't deal correctly with white space in file names. So you have to worry about quoting, for example. And you also have to ask questions like, what happens when this gets interrupted halfway through? And how do you parallelize this? I mean, sure, you can start up many conversion jobs in parallel. However, the access to the file system is still sequential. Here's the same job using the tools that we'll be talking about in this video. Notice that the processing script, the conversion, is actually the same. There are no worries about quoting or directories or white space. This code can actually work object store to object store. It doesn't require any data to be stored on the local file system. There's no problem if the job is interrupted, and it's easy to parallelize with shards. We will see how all of this works in the rest of the video. Let's look at some data in tar archive format now. Here you see a shard from the ImageNet dataset, shard number 130, and you can see that there are training samples that consist of a .class file, a .jpeg file, and a .json file. So the .class just contains the class number, the integer corresponding to the class. The .jpeg file is the image, and the .json file contains a lot of other metadata about this image. And the three files comprising the training sample, comprising the first training sample, are adjacent here. And then we have three more files comprising the next training sample, etc. Notice also that we could just use standard Linux tar or standard POSIX tar to look at this data. In fact, there are a lot of tools in Unix and Linux already for dealing with tar archives. For example, you can take this shard and just mount it on a local directory using archive mount. Now, the entire contents of the shard are actually available as individual files without having to unpack them. Of course, you can also simply unpack the contents of the shard. The primary command that we're going to be using for processing training data stored in tar archives is the tarp command. Tarp stands for tar processing. Tarp is a small, simple, and portable command line program written in Go. It's powerful and can deal with massive amounts of data, just like tar itself. It allows you to test and use your data processing pipelines locally on your local machine, and later you can scale up by deploying this in the cloud. Tarp itself is a statically linked executable, and you can usually copy it between Linux machines and just use it on the target machine. Let's start by building a little tool using tarp-cat. The tarp-cat command, just like the regular cat command, copies things from somewhere to somewhere, with possibly a little bit of transformation. So what we're doing here is we're saying that we want to take a slice of the input data, namely select the training samples up to training sample 18, from the ImageNet train.tar archive, and output those samples to standard out. Then we pipe this to the regular Unix tar command and extract them in the temp directory. Then we use the ImageMagick montage command to create a little grid of thumbnails consisting of the images inside the original tar archive. So that's the result. These are the first 18 images from ImageNet. We want to build a little tool to display images inside tar archives. And for that, we'd like the images to be displayed in the original order from the tar archive. However, by extracting the images into a directory, the display will order them by their directory listing order. To avoid this, we can use another feature of the tarp command, namely the rekey argument. And in this case, we're saying we want to rekey the files contained or the samples contained in the tar archive just by their number of occurrence in the input. So when we do this, we get an output tar archive that just contains samples numbered by their index inside the original tar archive. So the first sample is number 0, the second sample is number 1, etc. We can now write a little shell function that allows us to display a grid of images contained in a tar archive. We'll be using this little shell function throughout the rest of the presentation for displaying the effects of various kinds of image processing operations using tarp. So, as before, we use tarp cat to read some input file. However, the input this time is given on standard input, which is indicated by this dash. We tell tarp to rekey the images by their index, and then just give us the first 18 images. We extract all these images into a temporary directory, and then we use the ImageMagick montage command to generate a 9x2 thumbnail summary of the images in that directory, and then we display this in this worksheet. A note on the command line interface: the tarp cat commands and other tarp subcommands require both inputs and outputs to be specified explicitly. That's different from the regular cat command, which defaults to standard input and standard output when no arguments are given. This is because without explicit specification of inputs and outputs, it's easy to accidentally overwrite existing files and lose data. So you need to give an input. If you would like to use standard input, just use dash, and you always need to give an output with a -o option. If you want to use standard output, use -o dash. Remote data in tarp is handled via external programs instead of a limited set of built-in libraries or volume plugins like many other frameworks use. This method is a simple and flexible way of accessing any object store. It means that you can test authentication and performance of remote access programs easily by themselves, outside of tarp. Because of the use of sequential I/O and pipelining, it's actually efficient. And this mechanism works well even for datasets that are petabytes large. There are 3 basic mechanisms that we will discuss in the next few slides. You can pipe to and from tarp commands. You can use the pipe : prefix wherever you use a file name, and you can specify lists of files in place of a single file on the command line. Using standard input with tarp commands allows you to easily process data that's stored in the cloud. For example, here, the same ImageNet shard that we've been working with is stored as a compressed tar archive in the cloud. We download that shard in a streaming way using the gsutil cat program. We unzip it on the fly and then pipe it through the tarp cat command. In this case, tarp cat actually doesn't perform any processing, but later it will. And then we pipe it into our newly created show files program. Just see that we're getting the same set of thumbnails that we got from the local copy of the shard. Using pipes, standard input and standard output together allows us to process shards and datasets stored as tar files without using any local storage. For example, here we stream a shard from a Google Cloud Storage bucket. We uncompress it inline. We then use tarp cat to cut out the first 18 samples, and we store the result directly back into the cloud without using any local storage. And afterwards, we can retrieve the data that we just stored in the cloud and display it. As we saw, we can directly pipe to tarp's standard input, but we can also specify the same kind of pipeline by using a special syntax for file names. When a file name starts with pipe : then the rest of the file name is used as a command whose standard output will be used in place of an input file name. This convention is useful in combination with another feature of tarp, namely that we can specify input files as a list of file names contained in a file. Here, I'm generating a file containing a list of files referring to the 148 shards making up the ImageNet dataset. These files are specified using the pipe: syntax, followed by a command that will yield the decompressed tar archive on standard output. We use such file lists by using the -l option to the tarp-cat command. Here, the tarp-cat command opens in sequence all the files listed in the files list and then concatenates the sequence of training samples and outputs them to the standard output. And then they're passed to show files, which displays them. Here's another example of accessing the same storage data, but using the curl command. Using the curl command with the HTTP protocol is often more efficient than using the gsutil command. Here you see the same command in action using the new file list. For shuffling and sorting, tarp gives you a collection of basic tools. You can perform inline shuffling with a shuffle buffer. You can mix shards. You can sort entire shards. In the next version, you will be able to merge shards. And you can also distribute samples through ZMQ sockets. Of course, that's not what you really want. What you want is your data sorted or shuffled, and you don't want to have to think about it very much. Unfortunately, there is no single solution for sorting. Sorting depends on many factors. For example, how many cores and how many compute nodes do you have available? How much local and temporary storage is available? How much object storage is available? What's the size of your data set? What's the amount of memory available in each node? What are the OS and container limitations, like number of file descriptors open and number of network connections? And what are the requirements for output shards? The shuffle option to the tarp-cat command allocates an internal buffer. It adds incoming samples to that buffer and outputs samples from the buffer in random order. Shuffling changes the order of samples locally within a range of samples comparable to the size of the shuffle buffer. The shuffle option to the tarp-cat command allocates an internal buffer. It adds incoming samples to that buffer and outputs samples from the buffer in random order. Shuffling changes the order of samples locally within a range of samples comparable to the size of the shuffle buffer. Tarp sort is another subcommand that rearranges samples. It will read an entire shard, sorted by some key, and then output the sorted shard. The key can be the contents of any file specified by its extension, or it can be random, in which case tarp sort performs a complete random shuffle of all the files within the shard. As I was saying before, there is no single solution for sorting and shuffling. However, there are some common patterns. If you do all your processing on a single node, you can use tarp-cat with the mix and shuffle arguments and a list of input shards, and then pipe the output to the tarp-split command that we'll discuss later. If you have multiple nodes available, you use the same pattern, but split your input shards among nodes. Both of these patterns give you partial mixing, depending on the size of your dataset, the number of shards, and the number of nodes. If you need a more complete shuffle, you can repeat this process one or more times, shuffling the file list between each stage. For very large shuffles, you can also use the network I/O primitives described later. These take advantage of the very high capacity of networking switches for quickly moving vast amounts of data from source shards to destination shards. You can put together large-scale sorting networks similarly using tarp-cat and tarp-merge. There's a one-stop solution. Actually, there is a one-stop solution you can use for sorting and shuffling called AI Store. AI Store is an object storage server optimized for deep learning applications. AI Store understands sharding, it understands the record structure of POSIX tar archives and TF record, it can perform shuffling and sorting for you automatically even on very large datasets, and it takes advantage of disk and network layout. Sorting with AI Store is just a simple command line invocation. So why not always use it? Well, the reason is you need to install it, and your data is often stored in other object stores or in the cloud, and you have to sort it in those storage systems. So if you can use AI Store, it's a good solution, but if you can't use it, then tarp gives you other ways of sorting and shuffling your data. Efficient parallel and distributed processing requires sharding for reasons we've already discussed. This is usually handled by the tarp split command. As a result, processing pipelines often end with piping into tarp split. But sometimes you can omit it as an optimization, for example if you know that the output shards are going to be roughly the same size as the input shards. Tarp split is a subcommand that reads a stream of samples on its standard input and writes a sequence of tar archives to disk. Tarp split is used for sharding and resharding datasets. That is, it is used for splitting up datasets into approximately constant-sized chunks. Commented out, we see a pipeline that reshards ImageNet into 15 10 GB shards. For demonstration purposes, that would take a little too long, and here we just take the first 100 samples from ImageNet and split them into 2 shards with 50 samples each. Below, the 2 lines verify that we actually get 2 shards and that the first shard contains 50 samples. Usually, when converting datasets, we don't want to store them twice on local disk, once as files and once as shards. Instead, when a shard is created, we want to upload it to an object store or to the cloud. The --post option to tarp split makes that easy. It specifies a small script that gets executed after the creation of each shard. Here, we use the same tarp split example as in the previous slide. Using the --post option, we upload each newly created shard to Google Cloud Storage, allowing its disk space to be freed up locally. Often, after we create a dataset, files are in some non-random order. It's generally a good idea to store datasets in shuffled or random order. That's even though the data load in PyTorch will perform yet additional shuffling. We can do this by combining tarpcat with the --shuffle and --mix options with tarp split. The --mix option is limited by available memory and file descriptors, but you can usually mix hundreds or even thousands of shards on a high-end machine. And if you need even more mixing and complete randomization, you can run multiple stages of mixing, randomizing the order of shards in between stages. Let's now turn to the problem of processing individual samples. The tarp-proc command changes the contents of files making up samples and shards. It is similar to the map phase of MapReduce frameworks, like Hadoop. Now let's look at some actual processing of training samples. This kind of processing is performed by the tarp-proc command. Tarp-proc works a little like the xargs command in Linux. As an example here, we perform a file conversion with ImageMagick. Images in ImageNet are originally stored in JPEG format. Here we are converting them to PNG format using convert sample.jpg to sample.png. What tarp-proc will do internally is unpack each sample into a temporary working directory and use the base name sample for the entire collection of files that make up the training samples. This makes writing scripts that perform conversions or other manipulations really easy. After the processing script has been run, the -f option selects the file name extensions that will actually be copied into the output. Let's look at another processing example. Here we see the contents of shard 2999 from a sharded version of the YouTube 8M video dataset, a dataset consisting of about 6.5 million videos downloaded from YouTube. These video files originally are variable resolution and variable length. To use them as input for deep learning, we want to convert them into clips of about 10 seconds length and a standard size and resolution of 256 by 128 pixels. The conversion of the video can actually be carried out with a single command, but since this command is pretty long and complex, we're putting it into a script file. We're using ffmpeg for the splitting and for the scaling. Now let's apply the script to the shard. We stream the shard of videos from Google Cloud Storage. The actual tarp-proc command is very simple. We use the -m flag instead of -c flag to indicate to tarp-proc that the output from the script is multiple output samples with base names of the form sample-number instead of just a single sample as in the previous example. Note that we need to refer to the script by absolute path name since its working directory is different from the current directory. Its working directory is a working directory consisting of only the files making up the training samples. For this worksheet, we just process the first 3 videos and store the result in shots.tar. Inspecting shots.tar, we see that the script worked as intended. The clips actually end up nominally as subdirectories of the base name of the original sample key. We've already seen the tarp create command in the previous video. Tarp create assembles tar files from recipes. Each line in a recipe consists of a file name as stored in the archive, followed by a specification of the source of that content. In this example, we read two images from two different directories in the ImageNet dataset as stored in the file system. We also add two .cls files containing the classes of those training images. We can verify that the output looks as intended after running the tarp create command. When converting large file system-based datasets using tarp create, we can also pipe its output to tarp split to generate shards on the fly. So far, we've looked at processing individual shards. Processing individual shards is necessarily sequential since the data storage format is sequential. In order to process large datasets efficiently, we want to process many shards in parallel. This is quite easy using the toolkit we have developed, since the tools we have require no significant amount of local storage, and they can access remote storage easily through HTTP. Unlike many other tools, no configuration of network storage or network volumes is needed. In general, for large-scale parallel processing, we just write a small script like the process shard script above, and then submit it to a job queuing system for every shard that actually needs to be processed. The job queuing system will execute as many of these jobs in parallel as it can, and we often achieve a high degree of parallelism for processing the entire data set. There are many job queuing systems available. One of the most widely available ones is Kubernetes. Kubernetes runs on all major cloud providers, and you can also easily run it on your local machine using the micro-Kubernetes command. Kubernetes performs many functions in addition to job queuing. Computations in Kubernetes are specified in pod specifications. Pod specifications combine the specifications of containers, commands to execute, resource requirements, and other job-related information. This slide shows a simple Kubernetes pod specification for performing image conversion. Notice that it contains the same script that we used before for image format conversion. Note that in the shell script, we've replaced the shard number with a reference to a variable called item. This reference will later be replaced by the job queuing system. We can submit the job template from the previous example using the qpods command line program. Qpods is another small open source command line program written in Go. Qpod substitutes items in job specification templates, submits the jobs to Kubernetes, waits for all jobs to complete, and retrieves log files from jobs as they complete. Qpods works well with even thousands of jobs. Without going into much detail, let's note that tarp can also be used to create very large distributed processing pipelines. Here, for example, we start up 1,000 writer processes that will continuously receive samples via a ZMQ socket and write them to disk. After starting up these writer processes, we start up reader processes that read training samples from large collections of source shards and scatter them across the writers. ZMQ-style URLs can be used in most places regular files or pipes are accepted by tarp. At the beginning of this presentation, we noted that tarp is a potential alternative to MapReduce frameworks. In fact, you can build MapReduce-style processing pipelines out of tarp. A complete MapReduce operation in a system like Hadoop is roughly equivalent to a sequence of operations like tarp proc, tarp sort, another tarp proc, and another tarp sort. In fact, internally, MapReduce frameworks like Hadoop perform just these kinds of processing steps. Using tarp requires that you specify more of the details of how to perform such computations. That is, it's a lower-level tool. That means that you need to be a little bit more explicit in specifying your data processing pipelines. But in return, you get a number of advantages. You can scale to datasets that are petabytes large using thousands of nodes, or perform small-scale processing on your desktop with just a single command. You can test processing stages individually on your local machine, and even for very large-scale processing jobs, it's easy to track down failures when using tarp, since each processing step is simple and explicit. You can cope with resource constraints better by specifying where temporary files go, choosing between object stores and local disks, etc. And you can easily integrate other data sources and processing stages, something that in systems like Hadoop requires using plugins. For example, if you want to process data out of TensorFlow files, you can write a simple command line program, tf2tar, that converts TensorFlow files to tar files and then afterwards apply tarp for processing. Specifying these few extra details of a computation is pretty intuitive, since people writing processing pipelines usually have a good understanding of the resources they have and what they want to accomplish with their data. But of course, you can use both tools. Tarp is just another tool in your toolkit. So, in summary, the tarp command lets you manipulate sharded tar files consisting of training samples for deep learning jobs or other purposes easily and efficiently. Sequential processing with tarp is often easier and faster than equivalent file-based processing pipelines. With tarp and similar tools, you can test locally on the command line and then execute those processing pipelines in the cloud easily. Sequential processing with tools like tarp requires no network file systems, no volume mounts, and very little local storage. These tools work well with Kubernetes for large-scale processing of millions and billions of samples. And for scheduling execution on Kubernetes, you can use queue pods.